there's 5 problems from last week. Those are the ones I was talking about. And there's also 5 problems that I'm assigning this week. Just because I don't think we're going to be learning anything new today, just because of the vast amount of problems that there are, and also the vast majority of people either have not attempted because they were busy, which is completely valid, or they didn't get it after trying for a while. Alright, so there's a segment tree test, which I have a personal grudge against. There's Redox. There's grade 11 math. Math 137 at Squirreloo. And Wall. Okay. So we're definitely going to take up at least 2 of the problems, I think. Okay, so let's start off with segment tree test. Just because it's just called the segment tree test, so. Alright, so let's have a quick look. You have an array n of 1 to 100,000 elements, indexed from 1 to n. There are some amount of operations you perform in it. You either change the element, output the minimum element, output the GCD of all the elements, or output the number of elements equal to the GCD of the elements from the query range. And then at any time, every element in the array is between 1 and 10 to the power of 9. And then that's the problem. So I imagine out of those that attempted it, that you had the minimum range query was pretty simple, because that's the one I did in class some amount of weeks ago. And then the GCD query, if you know Euclidean algorithm or thought about it for a bit, you could have gotten this. And then changing an element, it's pretty simple, but there's some complications to it. And then after this one is the one that would have killed most people's submissions that they thought were really close to getting it. So let's get started. I'll just create a new REPL. Segment tree test take up. Okay, that is not the language. Okay, seg tree take up. Okay, quick question. Is my mic doing okay?
Your microphone is just fine. You are loud and clear.
Thank you. Okay, so standard include bit/stdc++.h, using namespace std, and then we're gonna have our main. Okay. So you have, obviously I assigned this because it's gonna be a segment tree problem. So I think I'm gonna need something with I'm gonna need something with the minimum value in the range and then the GCD value in the range. Those two I'm for sure gonna need. And then also the left and right at every point, or at every node. So I'm going to create a struct once again, and if you were not here 3 weeks ago, you should have watched the video, but that's okay. The struct that we make allows us to hold certain things, like if I have an array here, seg, let's say 5, this creates an array called seg with size 5 that has all the properties under the node struct. So if I have, let's say I want to have int left and right, or int l comma r, so every single thing has a left and a right, and then since I'm going to add a min val and then a GCD val, so I can every index, so I can use seg at 0 dot, and then I can access the left, the right, the min val, and the GCD val. Okay, so first off, what's the maximum array size? 100,000. So let's just go. I typically like doing constant ints for a maximum size. Constant int max n, because n is a variable, and we'll just say 100,005. And then obviously, well, not obviously, we said that the bound for a segment tree that will allow us to do stuff is if the segment tree has a size of 4 times the maximum array size. Let me just make sure I'm recording properly. Okay, I'm doing good. So that's all well. And then now we just have to have our array, or our initial array, that's going to hold the 100,000 elements. And not really going to do much else, but it's just going to make initializing a lot easier. So int array as max n. Okay, so let's just go and take our input. So we need our, first comes our n and m, and then the n integers, and then the m lines each contain in the format description above. Okay, so let's get input. Obviously, since we can, why not just use fast input? Syn.sync with stdio 0 and syn.die 0. Keep in mind, people have asked me, why don't you use printf and scanf? I just feel like that's kind of outdated and not really necessary, but it has its applications. And if you do use those, do not use the syn.sync and syn.tie, because if you don't understand how it's implemented, then you won't understand why sometimes it won't work, or it'll flush the output all at the end when it's not supposed to, or something like that. So if you don't understand it, don't even try using it. But if you want to do your research, that's all well and good. Okay, so we need to have our integers int n, m, and then we take our input. So syn n and m. Not whatever that was. Okay, and then after, we need to take in our input for the array, and just because they're indexed from 1 to n, to make our solution consistent with all the inputs, we could either 0 index the array and then just we can either 0 index the array and then just subtract all query things that we get in by 1. Like if we receive the left and right, we'd have to subtract it by 1 to index from 0 to n minus 1. Or we can just index our array from 1 to n and not worry about that. So I'm just going to do that instead. So for int I equals, so I'm starting from 1 because I want to 1 index the array. So the array at 0 just not going to be touched ever. So int I equals 1, I less than n, less than or equal to n, I plus plus, and I'm going to take cnri. Okay, so now we have our building our array. So now let's actually have our build tree function. And it's going to be quite similar to the build tree that we did with the minimum range query. So int, I like doing int v, int l, and int r. And then, so first we're going to assign our node at left and right, the node's left and right value to the value that we get in the function. So segv.l equals l, segv.r equals r, and then now we need to check if the left and right values are the same, because if we are, then we are at a leaf node, and when you're at a leaf node, you don't need to search down further. So if the left and the right are the same, then we need to assign these values. So what do you think I should be assigning these values to? Anyone can answer. So I'm going to take it everyone's either not listening, my microphone's really bad, or we're all confused.
Your microphone is just fine. I can hear you.
Okay. So I'm guessing we're all really confused. So the intention of the build tree function is to actually build our tree recursively, starting from the root and then going down all the way down to the leaves. So when we built our tree, the intention for our build tree is to have our root as the index 1 in the segment tree array, and then we want to build all the way from the left to the right. The left end of the array has index 1, and the right end of the array has index n. So we want to recursively build our function. We want to recursively build our tree. So once you keep building downward, 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 and then you reach a child or a leaf, which means that it can't be divided further, then these values can be assigned to something. So my question is, what can these values be assigned to? What is the minimum value of all array elements from L to R if L and R are the same?
Wouldn't it? Okay, you go.
No, you.
Pardon?
I'm telling Lily to go because she has a bigger brain than me.
Well, I want you to do it.
Oh, you just take whatever the array is at L,
Good.
since L and R are the same.
Yeah, because there's a same and you're only querying on one element, so that means the seg v dot min val is equal to array at L, and then at the same time the GCD is also array at L. And then because we don't want to build any further downward, we're just gonna
put min val instead of GCD.
Oh, that's a good point. Thank you. GCD val is equal to array to L. And then now we want to just return, get out of there, or otherwise you can just have an else, like I'm pretty sure I did else instead, which is also a valid way. If you don't want to put else, you can just put return here. And then if you put return there, you don't have to put an else because it's automatically going to break out of the entire, out of that, the build tree with those parameters, and going to move upward into what it came from. But if you don't understand that, you can just stick to the if else. So if we have the if else, we need to do something with going downward onto the tree. So we need a mid value. So we have to cut the node's range in half. And we did this last time by doing L plus R all over 2. And that's going to do integer division automatically. It's not like Python. And then we want to build tree the left and the right child. The left child has the next v times 2, L comma mid. And then so you're going to use the left half of the cut that you made, and then the right half, the right child has index v times 2 plus 1, and it's going to have the right half of the cut. So you're going to have mid plus 1 and R as your new range for your right child. So after you do this, you need to do something with, once you have 2 child nodes, you need to assign it to you need to use those to somehow make the parent nodes min val and GCD val work properly. So we've done the min val already. It's not that bad at all. Seg v dot min val is equal to min of the child's vals. So seg v times 2 dot val or dot min val, comma seg of v times 2 plus 1 dot min val. So this is grabbing the min val from the left child, this is grabbing the min val from the right child, and it's saying this current node's min val is the minimum of the lower value of the 2 child's min vals. So we have that, and now we need to do our GCD. Seg v dot GCD val. Is there a GCD built in? Does it work? Yeah, it might actually work perfectly. Okay, so seg v dot GCD val is GCD of. Now we just need the GCD of the 2 child GCD values. So seg of GCD dot seg of v times 2 dot GCD val, comma seg of v times 2 plus 1 dot GCD val. So this is saying the greatest common denominator of all elements in the left and the right is calculated by the greatest common denominator of all elements in the range of the left child, and comma the greatest common denominator of all elements covering the right child. So I'm not exactly sure if the GCD if the GCD function here is as efficient, but we'll find out. That's the adventure. And yeah, so that's going to be our basis of going to be able to doing the minimum and the GCD queries pretty easily. The query of Q is slightly different, and there are different approaches to it, but we'll get to that a little later. So for now, we're just going to do our simple minimum range query. Actually, first, let's do some work on the int main, getting our input and everything. So we have, so far we've taken n and m, and then we've taken the n integers representing the original array. So now we have, every query has the character for the query type, and then 2 values. They're usually left and right, except for the change one, which is changing the x element to v. So I'm going to say char q type, and then int v1 and v2 at the 2 values I'm inputting. And obviously those variable names can change. It's your preference. So now I'm going to take I'm going to do m queries. So I'm going to do a for loop for, let's say, int q equals 0, q is less than m, q++. So just some dummy value q, which is not going to have any significance to what we're doing. So cin q type, v1, and v2. So we've taken our query type and then 2 values. It's left and right for the 3 for the changing. It's changing the x array to a value v, or changing the v1th element in the array to v2, or it has the function. It has the left and right values. So we need to check. So first off, is the query type C? If q type equals C, then we have to do something. Else if q type equals m, then we have to do something. And then else if q type equals g, then we have to do something. And then otherwise, we know that this is the what's the query called again? The Q query, because there's only 4 options for the queries. So let's handle let's actually do the minimum query, because we've already done this before and it's probably the easiest. So so we need to make some calling some minimum query function. And this is going to allow us to, we're going to need a recursive minimum query function. If you have yours from last week, great. I'm not going to go and copy and paste it because I really don't know where the file is. And it's also better to understand why the query works and to go through the process of it every time, so you don't brain fart and forget it one day when you actually need it. So again, the habit of typing out your functions even though you know them, but it's okay if you don't want to. So we need our min query, where we're going to take the current index in the segment tree array, and then I like doing QL and QR, standing for query left and query right. So so you have a query left, query right, and then the index in the segment tree array. And so now I'm going to just take data, int l equals seg v dot left, and then r equals seg v dot right. Okay, so for people who remember, what is the first thing I should be checking in my min query function?
Wait, is it if they're equal?
If what are equal?
The left side and the right side?
No.
Wait.
I guess you could do that, but that's not really one of the cases that we talked about.
Oops.
But
Okay.
you're somewhat on the right track.
If there's no overlap at all.
Yeah, if there's no overlap. Because if there's no overlap, then why the heck should we return anything that's going to have any significance to the minimum range query? And that's why we're just going to return some really large value. So there's 2 ways to quickly check this, or there's 2 conditions to quickly check this. if the right end of the query is less than the left end of the node's range, if that is true, or the query if the right is less than the query left. So if the right end of the range that the node covers is less than the query left, then we know that they're completely non-intersecting. That's going to have no business in our minimum query, so we shouldn't return anything that will actually impact the final answer. So we're just going to return int max. So int max is the C++ way to write the largest integer that can fit in the int type. And this is, I believe, 2 to the 32 minus 1. I might be wrong. Someone please correct me.
31.
Pardon? Oh yeah, 2 to the power 31 minus 1. And if you calculate that, that's going to be completely outside the highest value that the array elements can take, which is 10 to the power of 9. So we're good. We're not going to have any problems with returning int max. So, okay. And I shouldn't return anything higher than int max, obviously, because otherwise it's going to go into the negatives because it's an int function, and you're going to return something higher than int max, it'll overflow and go into negatives, which is going to screw things over a lot. Okay, so we checked the case where it's completely, it's non-intersecting. Now for the second case. What is the second case?
If it's completely within.
Yes, if the node's range is completely within the query's range. So this is found by QL is less than or equal to L, and R is less than or equal to QR. I like to do this way, not any other way around, because it really looks like over here that query left and query right are just boxing around this L comma R thing, because we already know that L is always less than or equal to R, so it's kind of like this. If query left is less than or equal to the left, which is less than or equal to the right, which is less than or equal to query right, so you're kind of constraining L and R inside of query left and query right. So that's kind of a cool way to visualize it, and that's why I like doing it that way. So here, if it's completely inside the range, we want to return the node's minimum value, or the node's range's minimum value. So we want to return segv.minval. And then if they're partially intersecting, we said that, so if it's not fully intersecting or fully inside or completely outside, then we know that we have to traverse through the two children. So we just want to return, and the best way to do the minimum range is say min of the query from the left child and the query from the right child. So min query of the left child is index v times 2. The query left and the query right are going to stay the same because we don't want to change the bounds for which the query is going to be at. And then similarly, min query, and now the right child has an index v times 2 plus 1, and then ql comma qr. Okay, so does anyone have any questions up till here? This was done 3 weeks ago, but I understand 3 weeks ago is a long time, so feel free to ask if you need to. Okay, if not, that's good. So now we can move on to next our, okay, so actually we need to call our min query function. And that's simple enough, as we said that the min query, we always want to start at the root node, which has an index 1. So we want to print out the min query of starting from the root node, and then the bounds are L and R, which had v1 and v2 as their variable names. So cout min query v1 and v2, and then \n for new line, or endo if you want to do that as well. Doesn't matter to me. Okay, so that's the minimum range query. And now we need the Gcd range query, and then the changing element query. So let's just do the Gcd query because it's essentially the same idea as the min query. It's simply doing the same thing. checking the range if it's completely outside, completely inside, or partially intersecting with the query range. So we can just do int gcd query for our gcd query function, and then same parameters. We don't need to do anything special. Int v, int ql, int qr, and then I'm actually going to copy a lot of this code because a lot of this is going to stay the same. The thing that's going to change here is the return value, because that is not going to be necessarily the same as what it was before. Okay, so we need to think here. So this first case, we need to return something that won't actually impact the final answer. Like, it will be completely brushed off. What value should I return so that it doesn't actually impact the final answer of the GCD query? Remember, this is completely outside, so we don't want it to hurt the actual value. Okay, it's completely fine if you don't know, but okay, so the greatest common divisor of two numbers is the largest number that if you divide both of the numbers, both of the two parameters by it, you'll get an integer. So you should recognize that so every element in the array is between 1 and 10 to the 9. So we're not going to have a 0 value or a non-negative value or a negative value. They're all going to be positive. So that's a good thing to recognize. And we also know, or you should know, that 0 divided by any number in the any positive number is going to be 0. So if we return 0 here, then we'd be essentially doing GCD of 0, comma something. So GCD of 0, comma x. Well, we know that 0 divided by x is 0. X divided by x is 1, so that means the GCD of 0, comma x is x. So that means it's completely valid to return 0 because it's not going to actually impact the final answer, because the GCD of 0, comma x isn't going to change the value, isn't going to change x, which means that you won't actually ever have problems with the GCD value being messed up because you checked something that was out of range. So here we're just going to return 0. So so GCD 0, comma x is always equal to x if x is a positive number. Also works, so just GCD 0, comma x is x. And so that's why we're going to return 0, because it won't impact our final answer. Okay, so now second case, the node's range is completely inside of the query's range, so we actually want to return the value that's stored in the array, or stored in that node. So segv.gcdval. That's simple enough. Okay, and then same idea with the intersecting range, just not minimum range query. We just have to do a greatest common denominator GCD query. So GCD of GCD query of something, and that something is going to be pretty much the exact same as how we did it up here. So the left child has index v times 2, and the query range does not change. If you change the query range, it's going to mess up everything. So similarly, we did the left child, and then we have to check the GCD query of the right child. Has index v times 2 plus 1, and then the same query range. So this will be our GCD query, and then we just simply go and print it out. So since I'm lazy, I'm just going to copy this over down here and change this to GCD query. So this will print the GCD of all elements in the range v1 to v2. And that's going to work perfectly fine. Okay, so now comes the changing element query. And this we haven't actually covered, but it's not too bad. So when we change an element in an array, it's just as simple as accessing the array at the index. So it would be array at v1 equals v2. Very simple. Array at v1 equals v2. And we'll actually keep that here because it's not really going to slow down our program that much, so why not? But now we're working with changing an element in the segment tree. Because if we don't change it, then it's going to store the old value, which will completely screw things over. So now we need to see how do we change the elements properly. So changing an element means you're changing one of the leaves. The leaves that the L and R values are going to have index v1, the v1 that we get, because that's the index that we want to modify. So we're looking for elements, or looking for node in seg tree with range v1 to v1. And then once you're there, you need to update the value, the GCD value and min val of that node, because that node changes, and that node's GCD val and min val is only just going to be the value itself. It's going to only be v2 because it's only regarding one element, and the GCD of one element is just that element, and the min val of one element is just that element. So we need to update the GCD val and min val of that node, and then after we do that, we need to update the parents if necessary. And why this is necessary is, let's say you have two children. Let's say you have two children that have min vals as 5 and 8. And then, two leaves that have values of 5 and 8. And then modify the 5 to a, modify 5 to a 9. If you modify the 5 to a 9, the min of 9, 8 is 8. Whereas the min of 5, 8 before, min 5, 8 was 5. So we see how the minimum value in the parent array changes. And it's not always going to change, but there's cases for when it's going to change. So instead of dealing with cases and saying, oh, update only if your update value is greater than your old value, or something like that, if you can just update the parents if necessary, it's just going to be a really fast operation if you keep doing it in the recursive loop. So once you keep calling, after you change the node, you should just update the parents or reassign the parent values to how we assign them above here. Seg_v.minval and seg_v.gcdval. And by updating those parents, you're going to make sure that the parent values are updated, even if there were actually no changes in the min_val and gcd_val that you had to change of any of the parents. It's okay to run those operations just because they don't even take that much time. So let's actually implement this right now. So let's say, so we're not actually going to return anything this time. So it's just going to be a void. And let's just update. So int v and int index and int val, or int new val. So this is our update function. Okay, so we need to check now. Okay, so our target is to find the node in the segment tree with range v1 to v1. So we have to essentially find the element that has the left and right values are both equal to idx, because that's what we're passing in. So first, what I'm going to do is obviously get the left and right ranges, or left and right bounds for the current nodes, the current node. So int L equals seg_v.left and int right is seg_v.right. So simple enough. And now we have to find the element. And so this is the same process as above, where we kept searching, trying to find everything that was in range. And then if it wasn't in range, we just returned a dummy value. And once it was completely within range, we were able to return it or do something with it. And notice how we're doing query left comma query right as our update range or our function range or whatever we were trying to do. Our query range, my bad, not update range. Our query range. In the end, we're just doing a query range from IDX to IDX. So it's going to look very similar to this, except QL and QR are just going to be IDX and IDX. So first, we need to check if it's completely outside. If IDX is completely outside the node's range. So this is found by doing if IDX is less than L, or the right is less than IDX. Oh no, IDX is, wait, yeah. And so notice how over here I just replaced QR with IDX. The left and right stayed the same, and then I just replaced the QL with IDX. So hopefully you see the query, the similarity with the GCD and min query, and the update, how the ranges and the cases work. So if IDX is less than L or right is less than IDX, so that means that completely outside the range, and we need to do nothing here. We have no business here. There's no point in being here. And the simple thing you can just do is return. This will just get out of the update for these parameters and check the other side, or move on past this and check the other things that are held in the stack, because this is not going to do anything at all for us. And then now we can just do if left is less than or equal to IDX, and so just looking at this, we're replacing. Actually, okay. If all right, so you know that you're at a child node that has you know that the place that you're looking for is going to be a child node. So obviously it's going to be when left and right are the same. So if sorry, if IDX is left and IDX is also right. So this just means that we found a node where the left and right boundaries are both IDX. So this is the one that we want to update. Update the leaf node here. And then after, we want to have recursive calls. So updating the leaf node, as simple as just reassigning the GCD val and the min val. So segv dot GCD val equals, and then we stored it as new val in our function call. So new val. And then same thing for min val. Segv dot min val is equal to new val. Okay, and then after, we don't want to do anything here because we've already updated the child. We don't have anything to do below it, so we can just get out of there. Return. Okay, so now we need to do our recursive calls. And so the way we do this is, first, obviously, it's just going to be just calling the two children. Update v times 2, and the index range is going to stay the same, and the new value that you want to reassign it to is also going to be the same. Update v times 2 plus 1, IDX, and new val. So this is going to be updating the left and right children. So now we need to figure out this last step of updating the parents when necessary. So let's say, so we need to put somewhere segv.gcdval is the GCD of the two children nodes, and then segv.minval is the minimum of the two children node values. But we have to figure out when we should do that. So in this recursive calls, let's say I'm at the parent that's just above the target node, or the target thing that we want to update. So I update my child. So I go to the update called my child, and then it runs through this, and then it successfully hits the target, changes the value, and then gets out of there. So once it gets out of there, you'll be back at that parent that's going to move on to the next line. And obviously the next line is not going to do anything. One or the other is not going to do anything because it's completely outside the query range. So after the child gets updated, it comes back to after this. After child gets updated, you will be here for the parent. And this is the place where you want to update. To update the parent. Because the parent, the child gets updated, or like the child's values are reassigned, so then it comes down here, and then over here just before it leaves, because if there's nothing here, it's obviously going to leave. But if you just reassign the parent values over here, then you're guaranteed that all your parent values will update and will be reassigned if necessary. So here we're just going to do segv.minval is equal to the minimum of the two children's segv.minvals. So seg at v times 2 dot minval, comma seg at v times 2 plus 1 dot minval. Similarly, segv.gcd val equals gcd of seg of v times 2 dot gcd val, comma seg of v times 2 plus 1 dot gcd val. Okay. So this, the idea that you can update the parents right under right under your calls for the children's update functions is really important. It saves a lot of time. So does anyone have any questions with how I did this, or in general how I did anything with the update function? Because I'll be happy to go over it.
Are we not doing the third query right now?
We did the GCD query and the min query already. We're doing the update query.
No, I mean the one with the queue. Are we not doing that right now?
We'll be doing that in just a second.
Okay.
Okay, if not, then that's fine. We're ready to move on. Okay, so now comes the difficult part. Because, okay, so if we analyze the complexity, for the update function, you go through at most log n nodes. Or you go through O of log n nodes, because you either go to a node that isn't going to work. That's because you accessed it from the parent that was going to work, but you had to figure out which child was the right one to use. Or you got to the right place, and then you check the two ones below it, and then one of those two were going to work. So the time complexity for the update is O of log n. The time complexity we knew for a min query is the same time complexity because we knew that it keeps running down to at most O of log n nodes. It's slightly greater, like it could be scaling up by a factor of 2, but its overall time complexity is O of log n. Similarly here, O of log n, because it's the exact same process as the main query. And then building the tree, it takes a lot more time, but it's okay because you're only doing that operation once. So overall, if you're working with these three queries, your overall time complexity would be O of n log n, because this operation was O of n, and these three operations are O of, it wouldn't be O of n log n, but okay. So you have m queries, m for McDonald's. That's what I'm trying to distinguish m and n here. Each of these queries is O of log n, and then the build tree is O of n, big O of n. And then since there's m queries, for all of these if all the queries were min query, GCD query, and update query, or update function, then your overall time complexity would be n plus m times log n. And since m log n is bigger than n, then that means that your overall time complexity would be O of m log n. And that would work with the constraints here, 500,000 and 100,000. But now we have to work with our Q query. And this has to be done also. Each Q query has to also be done in ov log n or faster. You'll see that it's not going to be faster, but so we're going to target for ov log n Q query, and this is where a lot of people get stuck, and I was personally stuck on this for a really long time too. So we need to somehow do our Q query properly. So actually first let's. So here, no, not here. Let's just update our value over here just so that we don't forget later on. Update, and we want to go from the root of the tree. The x is just v1, and then the new value is v2. Okay, so now we need to handle a Q query somehow. And this is the difficult part of the question. Okay. So int, and then let's call it range count. And then the parameters are going to be int v, int ql, int qr, and then some value. So we need to decompose our query into two parts. First is results of the operation of glr right now. So obviously what you want to do is call glr. And after that, you want to output the number of elements from the lth to the rth index, inclusive, that are equal to g. Okay, so first part is get GCD for L, R. And that's simple as doing int GCD value is equal to GCD query, and then from the root, comma v1, comma v2. The exact same as how we did our GCD query up here. And now we want to do a range count from the range L, R, or the query range. How many are equal? How many are equal to GCD val or GCD value? And that's what this val is going to be. This val is going to be counting the amount. This will hold the value that we're deciding to equal to. Okay, so in the end we want to do we want to output a range count of starting from the root. QL is the same v1, v2, and then our values to look for equality is GCD value. Okay, so if we just hand-picked in an array how many are equal to some value, then the worst case time complexity is O of n. And we know that that's unsustainable because we want it to be at least O of log n, otherwise it'll be way too slow. So now we need to think of something different. Because if we do it naively, or even slightly if you do it only kind of optimized, it's not going to be enough to hit the target of O of log n, or get anywhere close to that. So the idea here is looking at a node, any node with some range L, R. All the values are going to be equal to some value, have to be equal to some value. All the values in the node's range have to be equal to some value to add on to the Q query. Actually, why am I doing this here? I should be doing this in my range count function. Okay, so first let's just take our data from our node. Int L equals seg v dot L, and then R equals seg v dot R. Simple enough. Okay, so there are a few ways that we can approach this. the first is, all right, a few things that we can, or actually a few things that we can notice. Few things to notice are, okay, first, if the GCD of a node is greater than val, that means if the greatest common denominator of a node is greater than val, then we automatically know that all numbers in the range are greater than val. Because if we think about it, we know that none of the values in the array have a GCD val of 0. Or no, we know that none of the numbers are going to be 0, which means that none of the GCD queries, none of the GCD val things in, okay, well, none of the data, how do I say this? In every node, the GCD val is never going to be 0. So we're never going to have a problem with, all the elements are 0. That means it will screw up the GCD val, which means we won't know how to get the GCD of all numbers. So, so that means that the GCD of all the numbers has to be greater than 0. Which means that the greatest common denominator is a factor of each of the numbers in the range. Which means that the number inside of each of the numbers inside the range have to be greater than val, because each of the numbers will always be greater than val, because if the GCD is something higher than val, and all the numbers inside of the range are greater than or equal to the GCD of the range, because the GCD is the factor of each of the numbers, then that means all numbers in the range are greater than val, and we can simply get out of there and we can say that there's 0 elements in this range L, R that will work. So let's actually know, so that's the first thing we know. So return 0 since it won't have any elements that are equal to val. Okay, so that's the first thing we need to notice. The second thing is, this also applies to segv.minval. What this means is, if all the numbers in the query range L, R, out of those, the minimum is greater than our desired value to be equal to, then we know that none of the values in there are going to be equal to val, because the minimum, if the minimum is greater than val, how can any of the other numbers be equal to val? Because they're all greater than the minimum value, or greater than or equal to the minimum value. So we automatically know that we can just return 0 if it's not going to be if the current node's minimum value is going to be greater than val. Okay, and then our final thing to notice is, now we need a few conditions for actually finding which values are going to work. Like, how do I know right away that if I hit a node, then all the numbers in there are going to be divisible, or are going to be equal to val? How do I know that every element in the range is equal to val? And there are a few conditions for that. So the first one is, obviously, the GCD val is equal to val. If the GCD of all numbers in there are equal to val, then we know that all numbers are at least val. But if we know that the maximum, we don't actually have this data in here. If we had a max val, the maximum of all numbers was also equal to val, then we can conclude that if all the numbers are in the range L, R, the max val is equal to val, that means that all the numbers are less than or equal to val. But we said on the left side of the condition here that all the numbers have to be greater than or equal to val. So that means that all the numbers are squeezed to be equal to val, or to a single value. And that's when we can return number of elements in the range L, comma R. Okay, does anyone have any questions up until there? Because this is definitely the hardest part to understand.
Would we have to make a max val for
Yes.
each node as well then?
Yes.
Okay.
There are other ways to do this, but I find this one the most simple to see. But either way, it's pretty obvious that if you're able to see all of this while solving the problem, it's pretty impressive because it's pretty hard to think of all of it at the same time and piece it together. So what I'm going to do is add max val to our node data. So at every place where I'm going to update the min val or do something to the min val, I'm also just going to do it to the maximum value as well. So I'm assigning my max value to array val. Now down here, segv.maxval is max of the left and right children. Seg of v times 2 dot maxval, comma, seg at v times 2 plus 1 dot maxval. And then the query won't change. It won't change the maximum value. The GCD won't change the maximum value. Here we need to update seg v dot GCD val, not GCD val, max val is equal to the new value. So every place where we update the minimum value, we're also going to have to update the maximum value because we know that we've changed something, and so so to always keep the maximum up to date on every node, we have to do it at all the locations. Let me just copy this and then change it to max val. So what I've essentially done is introduced a new variable, max val, and that's going to help me constrain all the numbers in the range to have the same value, and that it's all equal to val. Okay, so let me just make sure that I updated it and assigned everything correctly. Okay, that's good. That's good. And then in the queries, you're not worrying about the max val ever, so it's okay. And then we assign properly here, and then we assign it properly here, and then we add max val to our struct. So that's everything that we have. Okay, so are there any more questions with why I introduced max val, or how I did the range count at all, or how I'm going to do the range count?
Wait, Sat.
Yeah?
Does this mean you can also check if the minimum and the maximum are equal to the number you want?
Yes, that's actually what I did in my solution initially, I think, like when I submitted for the first time. Equivalent to segv.maxval equals segv.minval. Yeah, that would work perfectly fine. I think you can take any two of these and they would work. Yeah, if you take any two of these, they would work. But I'm just going to stick with the first two because I know I've already proven that they will squeeze to work. Okay, so let's go ahead and actually implement it. So we had two conditions. If the GCD of the node is greater than val, or if the GCD val of the node is greater than val, we know we're going to return 0. And also, if segv.minval is greater than val, we're going to return 0. So if segv.gcdval is greater than val, either of the conditions can be true. It's not both of them have to be true. Segv.minval is greater than val. Return 0. 0 means it's not actually adding on to the range count. And you actually, at the same time, you can actually add segv.maxval is less than val, because if any of them, let's just add it. Segv.maxval is less than val. Because if all the numbers in the range, out of all of those, the maximum number is less than val, then none of the numbers in there can be equal to val, so we can return 0. So let me just add that here. Also, if, okay. so that's our first condition. And then the second, and then you also have to check the overlap, like the overlapping conditions that we checked in our update, in our GCD query, and our min query. So if we're completely outside the range, so if QR is less than L, or R is less than QL, then you want to also return 0. Technically, I could actually just put all of these ORs into one thing, but that's just too much to understand at once, and it's going to be annoying to look at. So now we need to check if it's completely inside of the query range. So QL is less than equal to L, and R is less than equal to QR. And here, I'm going to take these two conditions. Okay, so we checked if segv.gcdval equals val and segv.maxval equals val. Then we want to return the number of elements in the range L, R. And that can be found by doing the difference between numbers and then adding 1, because you're subtracting the first element. So this gives number of elements in the range L, R. And then while I'm here, if you're inside of the range, but you're completely outside of, like if you're not satisfying the fact that segv.maxval equals val or segv.gcdval equals val, we can just return 0 because you know you can't split into any more elements. Actually, yeah. Actually, that's not even necessary because we've already handled that in the case where segv.minval is greater than val or segv.maxval is less than val. So that's not even necessary. Okay. And then below, we just want to return, below it's the case where some elements are intersecting, but we haven't hit any of the cases where we can return 0. So we have to add the sum of the queries from the two children. So return range count of v times 2, QL, QR, val, plus range count v times 2 plus 1, QL, QR, val. And that should do it for the range count. So what we do after that is, okay, actually we already did it, but just make sure I put an end line character. Okay, so let's test this out. Let's get some data. So our output should be 242. Okay, paste. 242, nice. Let's check sample input 2. I always like going through the sample inputs just in case I did it wrong or I have some obvious mistake. There's no point in wasting a submission on it. Alright, 2 and 3. So let's actually try submitting this and see if it works. Let's hope it does. What?
GCD is in C++17. Sure.
Okay. Okay, that's a good point. So if you're going to use GCD, use in C++17. If you have your own GCD thing, then that's fine. Great. Okay, so we got it perfectly fine with all test cases correct. Okay, so this is segment tree test. I'll just post in the chat, and also I'll work on putting everything on GitHub within the next few days. I know I have not been doing that at all. But okay, so here is the code for segment tree test. Let's not do that. Okay, so I can't attach it, so I'm just gonna upload the file. Okay. So that's the correct code, And make sure to use C++17. Use C++17 if you did not make your own GCD function. And really quickly, if we were a few years older and we didn't have C++17 in our day, let's think we have to use the Euclidean algorithm for the GCD function. So int fake GCD or old GCD. So if we wanted the GCD of two numbers, how would we do it? What is the fastest way to do a GCD function?
Euclidean algorithm.
And how does that work?
Okay, so you just do like GCD of A comma A mod B. Except like the okay, so you want
I'm pretty sure it's B comma A mod B.
He's right.
Oh
It's B
yeah,
comma A
same
mod
thing.
B.
Anyway, wait, but the A should be switched positions or something, so you don't like be done.
Pardon?
Oh, I didn't say anything. Oops.
Okay.
Unless
Oh, yeah. There's a condition here. What is the condition? Kevin, what is the condition?
if B is 0.
Okay.
Or A is 0, but if A is never going to be 0 if it doesn't start at 0, so.
Yeah. Return return A. Okay, so this says you're going to keep taking the modulus of A mod B and using the old value of B, and you're going to keep doing that until and you're like, so you're reassigning A to B and B to A mod B. You're going to keep doing that until B gets to 0, in which case you're going to return A. You can prove that it works, but I'm not going to do it right now. It was on the CSMC. You can think about it if you wrote the CSMC. And they were in different form, but it was equivalent to this GCD algorithm. So I'll paste this too, because why not? And Evan, what you said before, I've already finished that question about almost a year ago, so I'm not attempting it. I was looking at all the questions.
Sat is too smart for us.
I'm attempting one, it's hard.
Okay.
How many points is it?
Pardon?
How many points is it?
It's 20 points. It used to be 25, so yeah.
Oh, that's still pretty hard.
Well, supplementary questions I feel are like always really high up there. Okay, let's look at all these. There's grade 11 math. Oh, how confusing. Okay, so I want to go into a problem that has a different concept with updating, or like a concept to optimize updating. Okay, so
Never mind.
yeah, what were you gonna say?
I was going to say that nobody I don't think anyone attempted the DMOCC problem, but never
Yeah, that problem doesn't have it anyways. So it's okay. So we either should do redox or wall. I'll leave wall for you guys to do, and I'll take up redox. Because wall is a much more wackier. It's called lazy propagation. The idea is procrastinate on values that you have to update until you actually need to do so. So we're going to do, so wall, the thing is you need different lazy values. You can I use 2 lazy values in my solution, or you can implement it in different ways, but the lazy propagation for wall, nowhere near as straightforward as it is for redox. So we're going to take that up and introduce lazy propagation at the same time. Okay, so we need a new REPL. Our favorite language is C++, redox, take up. Okay. Yeah. Replic's got this bug. Whenever you create a new REPL, it's always black until you refresh it. Anyone else ever have that problem? No, it's just me.
I don't use REPL.
No, it never happens to me.
Okay, so looks like Replit just thinks I'm too old or just not good enough to use Replit. So I have to refresh the page one more time, which uses up Wi-Fi, which makes me sad. But that's okay. So let's have a look at Redox. Okay, so Luca is not paying attention in class again, just like Kevin Zhang is right now, while the teacher is explaining redox reactions. Instead of paying attention, he is playing with analog dials. An analog dial is a small device which always shows one digit between 0 and 9. It also contains a small button which increases the number by 1, unless it is 9, in which case it is changed to 0. Luca has n such dials on his desk, numbered from 1 to n left to right, and 2 sheets of paper for him to write on. Luca's game starts with him setting dials in the configuration and writes on the sheet. Luca then does the following m times. Choose 2 integers, writes them down first sheet, calculate the sum of the dials, and then press the button once on all the dials between A and B. Okay. Just as he finished the game, the teacher noticed him and took away all his dials on the second sheet of paper. Give him the contents of the first sheet, help him calculate the numbers on the second sheet. Okay. So, first thing we get is N and M. N is the number of dials, and M is the number of queries or operations. I'm going to call it queries. And then the initial configuration array, and then the query data. So let's get input. Or let's start a program. And then, so we have int n comma m. And then we need to have our int main. Oops. Set up our fast input. And we're good to go. Okay, so first thing we do is input n and m. Cn, n, and m. Okay, so it's like that, and then you just get a bunch of integers just right next to each other. Okay. So since n can be 250,000, that means this number or thing that you get is 250,000 things long. So I do not want to store it in a number, otherwise I'm going to be so incredibly screwed. So I'm going to store it as a, where am I going? I'm going to store it as a string. I'm going to call it a string s. Why not? Alright, so once I take the input, actually, you know what? String initial config. I actually want to use better variable names. Cn initial config. Okay. And alright, so the first step is write them down in the first sheet. Calculate the sum of the dials, number between A and B inclusive. Press the button once on all dials between A and B. Alright, so obviously we're going to need something to do with the segment tree because we're going to need a query sum and then a query update. Notice how I said query update this time. In the last question, we just did one update. Or not a query update, a range update. In the previous question, we only had to worry about updating one node, and then the parents just get updated to match the values. But now we have to update an entire query. So we're going to worry about that a little later because we can procrastinate along with lazy propagation. And I'll be explaining what that is once I get there. So structure of the node. So we need our ints of left and right. And then you can store the sum directly in there, but it's going to be really nuts to do so. And when you're at a node and you want to figure out the sum, it wouldn't even be that bad if you stored the frequency of all 10 things because you're only just doing 0 times the number of zeros, 1 times the number of ones, 2 times the number of twos, so on to 9 times the number of nines. So, and that operation that's 10 operations, which is big O 1. So I'm actually going to store the frequency int freq I'm going to store the frequency of each of the numbers 0 to 9 in the range. Frequency of numbers. And we're going to say our max size was what? Our max size was 250,000. So I should have a constant in max n. 250,000, and I'll just do 250,005. So this size is going to be seg of 4 times max n. And now, so once we have that, we need to have our initial config, and now we're ready to build our tree. Void build tree, int v, int l, and int r, which is the current index in the segment tree, the left and right that we're going to assign to the node. So segv.left is L, segv.right is R, and then simple, just as last time, if left and right are the same, and then the otherwise we need to do something else here. If left and right are the same, we need to think about how we're gonna actually we need to actually assign all the values to 0, because initially the frequency of everything is 0 except for the one thing that you have in your current string per se. Okay, so if left and right are the same, then that means we need to initialize all values. Actually, you know what? I'm just going to use memset. Memset freak 0 size of freak. And if you didn't want to do memset, oh no, it's not freak. It's segv.freak. If you don't want to use memset, you can just loop from 0 to 10 of and set each index, the value at each index, to be 0, and that's perfectly fine as well. So we just set the values. And now we have to actually update with increment 1 for the value itself that we're covering. So the string was initial config, and what is this? Is this 1 indexing? Okay, yeah, this is we're going to be 1 indexing again. So for all the integers, we're going to be 1 indexing. So instead of so it's better to just do the same idea of 1 indexing our tree, but we don't have to worry about that right now. So we can just do, actually, the 1 indexing will matter right now. Segv.freak at some index has to be 1, because the frequency of everything is 0 except for one thing is 1, because there's one thing in the range. So that means it has to be one thing that has a value of 1. So we need to work with initial config of the index is L in the array, and the frequency of the number is 1. Okay. Actually, L minus 1 is going to be 1. And the reason I do L minus 1 is because when I do my build tree, let me just do the build tree right now. Since I want to do a 1 indexing, the tree roots can always be 1, and then I'm going to be going from 1 to n. And so I want my first thing to be 1, but the string indexing is 0. So that means I want to have 1 minus 1, which will map to 0. So initial config at 0 will get the first character, because I'm going to make L1 at the start. So since I'm 1 indexing here and the string has 0 indexing, I'm going to subtract 1. So segv.freak at initial config at L minus 1 is 1. But the problem is initial config at L minus 1 is a character. So we need to actually do something to convert to an integer. And I just like doing minus 0, because a character minus character returns the ASCII value minus ASCII value, which will be the correct integer from 0 to 9. This is a cool trick that Mr. McKenzie actually talked about briefly last year. But yeah. So we went and changed the frequency of that 1 to 1, and then we're good to go. for now at least. We have to do some lazy propagation, but that's going to be saved till later. So int mid is L plus R over 2. And then now we need to just call our build tree for the two children, v times 2 left comma mid, bisecting on the left child and taking the left portion, and then the right portion for the right child, mid plus 1 to R. Okay, and then once we do that, you need to realize that the frequency for the parent for each number from 0 to 9 is the sum of the frequencies of the two children, because it's the total number of zeros is the total number from the left child plus the total number for the right child will be all for the parent. So we have to do loop for int I equals 1, or int I equals 0, I less than 10, I plus plus. We want to do seg v dot frequency at I equals seg v dot frequency, seg v at v times 2 dot frequency at I plus seg at v times 2 plus 1 dot frequency at I. Okay, any questions with how I built my tree? Because this is slightly different.
Wait, can you talk about line 19 again?
Line 19? Okay. So, alright, the first part we're going to worry about, okay, so the character -0 is to convert to an integer. So that's, that converts the characters to its ASCII value minus the character 0's ASCII value and subtracts them. So that's that part of it. And you already know that the ASCII values from 0 to 9 are consecutive, so this is going to work and give us 0. And the reason I do initial config at L minus 1 is the L is because left and right are the same, and that's for the current index. But since I 0 index the initial config string, and I 1 index my array, or what I want a 1 index for my queries, that means I have to do L minus 1. So like when I built my tree, the leftmost element had a value 1, but the leftmost character in the string has an index 0. So that means if I did 1 minus 1, it would give me initial config at 0, which is the leftmost character in the string.
Okay.
Okay. Any other questions? Okay. If not, then we're ready to proceed. So we want to calculate the sum of the numbers. Alright, so we need to get a query here. So let's look at the size of the numbers. So there's at most 250,000 numbers, and if they were all 10s, it'd be 10 times 250,000, which is 2,500,000, which will fit inside an integer, I believe. So we're good to just use integers. So int sum query, I guess. So int sum query. So for the current node in the tree, or the current index in the tree, and the query left and query right. So we're working with A to B. Okay, so same idea here. Let's grab our left and right. Int L equals seg v dot L. R equals seg v dot R. And then we're going to do the same thing where we check the first condition we check is outside of the query range. So QR is less than L or R is less than QL. And if so, we don't want to add to the sum and we don't want to affect the sum in any way. So we know that adding 0 won't actually affect the sum, so we're just going to return 0 because we know that the sum query is going to be additive. And then if QL is less than or equal to L, or and R is less than or equal to QR. Okay, so in this case, we want to find the sum. So that means everything in here is valid for the query, and we want to find the total sum of everything. So the way you find, all right, so the way we're going to do it is for every thing in range 0 to 10, for int I equals 0, I is less than 10, I plus plus, we do, that's not good. We want to do adding to some sum. Actually, let's create a sum variable, int tot equals 0. And then we do tot plus or equals, and then we want to multiply the number on the pad times its frequency. So it'd be I times frequency of I. So if there was like 15 nines, then we'd have to do 9 times 15, and not frequency of I, but seg v dot frequency of I. And while we're in, and we cumulatively got the sum, and then we just return that total. And then after, if we're not complete intersecting, or complete inside, but we're also not complete outside, then we can just return the sum of the queries from the two children. Sum query v times 2 for the left child, query left and query right will not change, plus the sum query for the right child. QL and QR will not change, and the right child has index v times 2 plus 1. Okay. Are we good up until this point?
Yes.
Okay, that's good to hear. Someone answered. Okay, so we calculate the sum and write down the sum on the second sheet, and then press the buttons on the dials between A and B once. Okay, so let's actually just take the rest of the input first before we talk about lazy propagation. So we have m queries. So for ints q, I guess, q for query, q equals 0, q is less than m, q plus plus. Now we need the data, which is literally just choosing two numbers a and b. Okay, so int ab, and then take a and b as inputs. And then, so first thing we want to do is print the sum query out. So we just do cout sum query of starting from the root, index 1, and then from A to B, and just print that out. So now we have to work on updating a range. Okay, so the scary part about updating the range is, so thinking about when we were just updating elements in segment tree test, is that when you update one node, you're able to go down through O of log n like edges to the leaf of the segment tree that we want to update, and then when the recursion is done, it just traverses back up and it will update. But if you did a range update, then the problem is you have to keep updating all the children with all the values. And the problem with that is you're going to have to keep doing O of log n operations for every element in the array, or for every element in the range. And if the range was 1 to n, then that means your time complexity for one update would be O of n log n, which is miles too slow for 200 miles too slow for one operation. Because if one operation was O of n log n, then all of the operations total, the worst case is O of mn log n, which is way too slow. So updating a range is going to be using a technique called lazy propagation. Okay. Makes updates much faster. Lazy propagation. And the idea behind lazy prop, I'm just going to call it lazy prop because I'm too lazy to type, and I don't want to spell wrong every single time. So the idea behind lazy prop is you want to save updates or procrastinate on updates as much as you can. This means, like, let's say you had to update a node, and then you updated a node, like you went here and then you pressed the button once on a node that was valid, and then you never ever actually access that node for a really long time. Let's say you never access that node ever. Theoretically, you never actually had to update the node value because it's not really necessary to do so. Like, if you never update a node value, how do I say this? If you never actually access that node ever again, then that means that that node value, there's no point in going down and updating all the nodes below it up until their leaves, because you weren't actually ever going to access it ever again. And so that was pointless. You just wasted a bunch of time, and you just had done a bunch of extra operations that you never needed to do. So lazy propagation takes advantage of that. It holds updates and does them later. And the time where you access a node is in your sum query, and when we have our update function, it's going to be doing in that too. But besides in those function calls, you're never actually going to access that node, so there's no point in updating the children if you're not ever actually going to need to use it. And so the idea of lazy propagation is procrastinating on updates as much as you can, holding them until later guarantees that you have best performance, because anything that is not necessary, you will never do. And even if things are not necessary, or if things are necessary a lot later, right, or if you get to, how do I say this? If you get to pressing the button calls, if you ever get two update calls, or two things that you have to update, you still never, you can just add the lazy propagation, you can add the lazy values together and do them later. So it's like saying, if you have, if you're given an assignment that's due on December 15th, and then you're given another assignment that's due on December 16th, don't even start them until it's December 14th or December 15th. Don't actually do that, people. But that's what the program's going to do. It's going to keep collecting the lazy. It's going to keep collecting update things or queries that you have to update, or things that you have, like something warning you that, hey, you have to update. And it's not actually going to do them until they get accessed. And so when they get accessed, you update them, and then you do the operations on them. So if you ever have multiple things, or actually not two, if you ever get multiple things you have to update on the same node, you can add the lazy values together and do them all later. When you actually access that node for a query. So procrastination really saves a lot of time here, or lazy propagation. Note that I do not condone doing this, but I do not condone doing this in real life, but it's fun to do in programming. But in reality, a lot of us do it, unfortunately. But yeah, so that's lazy propagation. Now let's see how it works. So you're going to need some lazy value. And we're just going to call it lazy because why not? And then initially, you're not going to procrastinate on anything because you have nothing to do, ever. Like at the start of the program, you never had any assignments to do or anything like that. So segv, actually not even here, because every node's lazy value is going to be 0. Because at the start of the year, you're really happy because you're not procrastinating on anything because you have nothing to do. So in segv.lazy equals 0 at the very top. Now we need to actually think of, we need to actually see how it gets implemented in real life, or in our program. Okay, so we're going to create our lazy function, or the thing that we update the lazy. So the idea behind the lazy propagation specifically in this question is you want to change the lazy propagation you're going to do here is pressing the button once on all the dials between numbers A and B. So if you're at a node and you have to press the dials between A and B, that's the same as telling the two children of yours to press the dials that many times between A and B. And so segv.lazy, this holds the number of pending presses to do. Okay. So void push lazy. And this is just going to be, this is something new. So int v. So what this function will do, this will update the current node and give the lazy values to the two children. And by that way, what you're essentially doing is you're not actually going to ever do something in advance. You're always going to do something when you need to call it. So if out of your friend group, let's say like some person has to do an assignment, but none of the others, but it's like in an order of a presentation, you're going to hand over the baton of, hey, you can wait until later because I'm going to update myself right now, or I'm going to do this presentation right now, but you can keep procrastinating. So that's what the push lazy function will do. So same as this common thing between the functions is that we're going to need to have our left and right, and we need to change the frequency somehow. So we're going to do that last. Okay, and then now down here, so we're going to somehow change the frequency. So we're going to have some function or some method or whatever we do. And then after, we're going to be pushing lazy values to children. Okay, so when we push the lazy values, the number of operations that a current parent has to do is also going to be the same. You also have to add that on to the number of operations that the child has to do. So you're going to add on the lazy value of the child. You're going to take the lazy value of the child and add on the lazy value of the parent. Plus segv.lazy. And then at the same time, segv times 2 plus 1 dot lazy plus or equals segv.lazy. And the reason I'm not doing equals segv.lazy and I'm doing plus or equals segv.lazy is because I may already have some updates that I have to do, but I'm saving for later. But who cares about them doing them right now? I'm just going to save them all for later by just adding on segv.lazy. I'm not going to reassign the values and update those. But what I am going to do is, like in the section over here, like what I'm going to do over here somewhere is create some, change the frequency somehow at that node. We'll worry about that later. Get the idea here, just waiting till later for everything. So after you get to here, you need to set the current node's lazy value to 0 because you've changed everything with the node, and you changed everything with the node. You've passed on your laziness to your children, and so now you have nothing to update. You have nothing to procrastinate on. So you're back at no procrastination, lazy equals 0. And then after that, you're done. But the only distinguishing case here is if L equals R, or if you're at a leaf, then you know that you will never actually have any children to update. So if we have if L equals R, then we have no children to update. And if we have no children to update, all we just have to do is assign our value as 0, and then we can just get out of there, because there's no point in doing anything else. So now comes the difficult part, or the quote-unquote intention of the question, where you have to change the frequency of change the frequency or modify the frequency somehow. And so here's the thing: when you press the buttons once, you shift all the numbers 1 to the right, and 9 goes to 0, because 9 can't go to 10 because 10 doesn't exist. If you shift it twice, you move everything right too. If you shift everything 10 times, however, you're going to end up at your original position, which means that there's no point in letting your lazy value get higher than 10, because every multiple of 10 that you have is just going to cycle back to the beginning. So what we can do here is, when we add on our lazy, is we just say seg v times 2 dot lazy mod equals 10. So here we remove unnecessary cycles. And same idea for the right child. Seg v times 2 plus 1 dot lazy mod equals 10. We remove unnecessary cycles by doing mod equals 10 for everything. So now we need to actually worry about changing the frequency, because we realize that we don't have to do anything lazy that's higher than 10, or that's a multiple of 10, and we just remove the cycles. So changing the frequency. So let's say you have for index 0 to 10, let's say you have 1 3 0 0 4 7 4 6 5, that's 7 numbers, 0 0 1, and you want to shifted right by 3, and so your target value is moving everything 3 to the right. So okay, so this 0 over here is going to move 3 to the right and come right back up to the beginning. So the first thing is going to be 0. And then the next thing is going to be this 0 over here. And then the next thing is be winding this 1 3 to the right. And then after this one over here, we'll be just moving 3 to the right. 1. And then the idea is 3, 0, 0, 4, 6, and 5. So we shift right. So this is the shifting right by 3. And this would be the new assignment, the new frequency array. So modifying it all in one is going to be really hard. So what I'm going to do is just have some temporary array, just so that I can easily assign it without messing it up, and then assign segv.frequency to be temp. So how it's going to work is, so segv, just to make sure I don't think I'll ever actually need this, but segv.lazy mod equals 10, just so that I don't actually have any problems with cycles. So what I'm going to do here is, for int I equals 0, I is less than 10, if I could type, I is less than 10, I plus plus, the frequency, the temp frequency at I, this is the temp thing is going to be our new frequency array. Temp at I is going to be equal to seg at I minus the amount that you have to shift, or the segv.lazy, the amount that we had to shift everything by, or dial by, segv.lazy. But the only issue with this is that if I is greater than segv.lazy, then we're going to be in trouble. Because, no, if segv.lazy is greater than I, we're going to be in trouble. because then you're going to be accessing from a negative index. And what's the issue here? Oh, my bad. segv.frequency of I minus segv.lazy. And so instead what we're going to do is if we did this modulo 10, for some reason, negative numbers mod 10 in Python and Java, they're still negative. So instead what we're just going to do is plus 10. Because I know I minus segv.lazy is going to be less than, or it's always going to be greater than or equal to negative 10. So if I add on 10, I minus segv.lazy plus 10 is going to be greater than or equal to 0. And just in case, I'm going to have an extra mod 10 there. So I assign everything from the shift, which is segv.lazy. And then after, I just I just loop through the indexes from 0 to 10. And I just simply do segv.frequency of I equals temp at I. Because we don't want temp to be our new thing, because the thing that's stored, because the frequency array is stored as freak in the segv struct. So we're just going to use, we're just going to assign all the temp I things to frequency of I. Or no, other way around. Assign all the frequency of I values to temp at I. So that's going to be our push lazy. And now we can simply just do our so this is the push lazy. This will help us with shifting everything and also pushing updates downward. So now all we have to do is create some update function. Int v and then you need to update from some range, update left to update right, which is ul to ur. And this will call push lazy if necessary, and we'll see when we should call it actually. But this will the update function will specifically just work with adding on to the lazy propagation, and then that's all it's going to be. So we need to just use our int l as segv.l and the right as segv.right. And the simple cases here still apply. If the update range is outside of the query, if the node's range is outside of the update range, then we don't have to do anything. It's completely unnecessary. And then if your update range fully contains your query range, here we just add on to our lazy, segv.lazy ++. And what we're doing is we're telling this node, hey, we have an update for you, but we're going to save it for later. Or you can save it for later because we don't actually need you right now. But just in case, also here, because we don't want to have any unnecessary cycles, we're going to do segv.lazy mod equals 10. And then now we can just return. And then after, if it's not completely inside or completely outside, we know it's intersecting, so that we have to call the update to the children, because those will potentially be inside completely or outside completely, and so it will get pushed down. So update for the left child and the right child. And then after, just like how we did in the previous question, how we took the values and then we updated the children and then reassign the parents' values if necessary, we're going to do the same thing here. So for int I equals 0, I is less than 10, I ++. We need to set the frequency at I based on the sum of the frequencies of the two children for every index. So segv.frequency of I equals segv times 2 dot frequency of I plus seg at v times 2 plus 1 dot frequency of I. And then after we're done, And I just realized I haven't asked you guys in a long time. You guys are you're probably completely lost. How many of you guys are completely lost? Let's actually go to polls right now. Or are you completely lost? Alright, so if you're still here, please go vote in the poll if you're completely lost, because I just realized I did not stop at all. Person shrugging. Okay, so no one understands it. And that's understandable. I completely forgot that there was an audience here, so I really should have slowed down. Okay, so the only person that gets it, or the only people that get it are Lily and... Alright, so David just unreacted. Alright, David's just gonna mess with me. That's fine. Okay, I'll probably finish this next week because...
You get it, but you don't like completely understand it. Yeah.
Yeah, that was definitely where I was when I was first learning this. Okay, yeah, I think I'll just save this for next week. We might go back. We might even redo like half the question, or the entire lazy propagation part of the question, because I completely at like I don't know, was it like 5:05? I completely forgot to keep asking people if they were completely lost, or if they were like doing okay. And I just explained the entire lazy propagation thing without doing that, which was definitely my fault. Okay, so I'll probably go over this next week. I'll post what I have so far, but it's not fully completed. And yeah, so your homework for this week, if you can, I recommend working on the questions from that were assigned before and doing those before you attempt these next 5 questions, because I'm pretty sure there are only a few that I actually thought were doable. Actually, yeah, Laylee contest was easier, so you can do this. Okay, so try the problems from last week before you try these problems, because other than the one I said you can do this, but I say you can do this, but you also need to know lazy propagation for it, so that's not good. Yeah, so I'll probably go over lazy propagation again next week.